Quasi-static processes. Imagine a system which is at thermal and mechanical equilibrium with its surroundings. In this state, its temperature is the same as that of the surroundings, and so is the pressure. Let us change the pressure of the surroundings to a lower value than it was initially. This would result in a sudden change in pressure of the system as well, until it gets to an equilibrium state again. During this change in pressure, the system may pass through several non-equilibrium states before it finally gets to an equilibrium state. Similarly, when the temperature of the surroundings changes drastically, the system tries to get to thermal equilibrium again, but when it does so, it passes through several non-equilibrium states. These non-equilibrium states are difficult to deal with because the values of the state variables are unpredictable at these states. It is thus convenient to imagine an ideal system in which all transitions of state have only equilibrium intermediate states. Such a process is infinitely slow and is hence known as a quasi-static process. Variables of the system change extremely slowly, staying in equilibrium with the surroundings all the time. In a quasi-static process at every stage, the state variables differ from the surroundings only by an infinitesimally small amount. Such a process is hypothetical in nature and is not possible in real life. Depending on the variable held constant, processes may be divided yet again into different kinds. For a process occurring at a constant temperature, the term used is isothermal process. If a process occurs at constant pressure, it is known as an isobaric process. Similarly, if it occurs at constant volume, then the process is known as an isochoric process. If there is no heat flow between the system and its surroundings, then the process is known as an adiabatic process. For an isothermal process, the ideal gas equation is PV equals constant. Assume that an ideal gas goes isothermally at temperature T from its initial state P1 V1 to the final state P2 V2 at any intermediate stage with pressure P and volume change from V to V plus delta V. We have delta W equals P delta V. Since delta V tends to 0, we have W is equal to integral of P dV from V1 to V2. This equals mu RT integral of dV by V from V1 to V2. This equals mu RT ln V2 by V1. From this equation, we can see that in an isothermal expansion, the gas absorbs heat and does work, while in an isothermal compression, work is done on the gas and heat is released. We know that in an adiabatic system, there is no heat exchange between the system and its surroundings. For an adiabatic process, PV raised to gamma equals constant. Here, gamma is the ratio of specific heats at constant pressure and constant volume. Thus, gamma equals Cp by Cv. Thus, if an ideal gas adiabatically changes its state from P1 V1 to P2 V2, we have P1 V1 raised to gamma equals P2 V2 raised to gamma. The plot here shows the PV curves of an ideal gas for two adiabatic processes connected to two isothermal processes. Thus, work done in an adiabatic process to take a system from state P1 V1 T1 to the state P2 V2 T2 is given by W is equal to integral of P dV from V1 to V2. This equals constant times integral of dV by V raised to gamma from V1 to V2. This equals constant times V raised to minus gamma plus 1 by 1 minus gamma from V1 to V2 is equal to constant by 1 minus gamma into reciprocal of V2 raised to gamma minus 1 minus reciprocal of V1 raised to gamma minus 1. This constant may be P1 V1 raised to gamma or P2 V2 raised to gamma. Therefore, W is given by the following expression. W equals 1 by 1 minus gamma into P2 V2 gamma by V2 gamma raised to minus 1 minus P1 V1 gamma by V1 gamma minus 1 equals 1 by 1 minus gamma into P2 V2 minus P1 V1 equals mu R into T1 minus T2 by gamma minus 1. From the equation, it can be seen that if work is done by the gas on the system, its temperature falls, while if work is done on the system, its temperature rises. In an isochoric process, the volume V of the gas is constant. No work is done by the gas or on the gas. All the heat absorbed, thus, goes towards changing the internal energy and the temperature of the gas. In an isobaric process, the pressure P remains fixed. Work done by the gas is given by W equals P into V2 minus V1 equals mu R into T2 minus T1. The change in temperature results in change in the internal energy. Heat absorbed partially goes towards increasing the internal energy of the system and partly towards doing work. In a cyclic process, the system eventually returns to the state that it originally started from. Since the internal energy of the system remains unchanged, delta U equals 0, and the total heat absorbed by the system equals the total work done by the system.